Hello guys, my name is Arun Tyagi and today we are going to discuss about Raft. So in distributed system, uh, we talk about components like distributed cache or a job scheduler or service discovery, right? In all those things, we talk about things like we will keep all the node in consistency that they have the same state, right? And for consistency, we can use things like quorum, or we can do like one leader, which is responsible for making the same state of the followers as well, right? So so things like how exactly we choose a leader, and not we, how system chooses a leader. What if leader fails, goes down, that particular node which is acting as a leader goes down, or how exactly this replication of state in all the nodes actually happens into a real system. So that is where our consensus algorithm come in picture. So Raft is one of the consensus algorithm, and this is actually these days gaining a lot of popularity, and it is actually easy to understand. It's made for so that we can understand it easily. In your system design interview, if you have ever talked about, I'll use Zookeeper for service discovery. By service discovery, we mean is which service I should call right now for this particular call. Maybe, because of that particular hash or something else, right? The decision can be based on anything, but making that decision. So behind the scene, those are powered by something like Raft or Raft. Right? So on real life systems, so some of the big services, if you might have heard of, etcd, that is inside your Kubernetes, where your config lies. So that is how your Kubernetes decides to which particular node I need to go for that particular thing. So that entire config is in etcd, and that is running on Raft. Then CockroachDB, it's your SQL DB, actually, a distributed SQL DB that also runs on Raft. And then this particular thing is same as for service discovery, right? So all those things runs on Raft. So in this video, we are going to talk about what is Raft, how we are going to do, how exactly we do your leader elections, how exactly we replicate the state in all the nodes, and what if the main node, the leader dies, what exactly happened, how system recovers from it. Let's learn it from the angle if we have to design a system like a Raft, how we will achieve it, and that way we'll learn, low level details of it. So what exactly this system offers, as in terms of the functionality. So our functional requirements will be election of a leader, like I said earlier, replication of state, or here we actually call it replication of logs, in every node in that particular for that particular service. Then maintain the strong consistency, and then handling of node failure. Obviously, physically those nodes will fail, but overall that system should look like it is working, right? So fault tolerance should be there. That is actually a functional requirement here in something like Raft. When coming to your non-functional requirements, high availability, because obviously these systems are like on which the services depends. So if these systems, if availability is anyway lesser, it will impact the overall service. So higher availability, fault tolerant, again, uh, you can think of something like quorum should be there behind the scene, right? That these many systems, some n number of systems should be having that data in exactly same state, so that entire you can say that entire service which is having these replication ultimately gives you exact identical result to every caller or every client. minimal split brain scenario. This is because we are talking about election of a leader, right? So there are chances when leader dies, there are chances into the system when multiple nodes which were follower and now are candidate of becoming a leader, they can at the same time start thinking like we are the leader. So that in general life called as split brain, when multiple people thinking that we are a leader. So that scenario should be as minimized as possible. And how we will recover from that situation, that should be your another non-functional requirement. And finally, durability. So basically, whatever log are coming to the system, those should be flushed or written into that onto the disk. So then only we can say it's durable. So even if your computation is dying, your node is dying, this, all the logs towards the system are saved on disk, so you can recover at any point of time. So these are my non-functional and functional requirement. Okay, let's talk about the first functional requirement which we are having, which is about the leader election. Let's see on a very high level how exactly it happens. So consider it as a beginning state, or this state can occur at any point of time into the life cycle of that particular system. So all the nodes right now are followers. But there is one thing which is running in internally into that node, is that there is a threshold point or a timeout which is random, different for every node, at which if there is no request coming from any leader, so it converts it itself into a candidate. Now, what that means? So, let's suppose at S1, it converted itself after a timeout into a candidate because there was no request coming from a leader. So, what it does is it actually sends request to all the known nodes that, and request is like give election, leader election. So election vote or give me vote. Normally this runs on RPC. That means you are connected to all the system and you are using a remote procedure sequence to execute it. That is the fastest way of doing it. So over RPC, you literally send execute a method on all other nodes for the to get the vote, right? And it sends to everyone. It's possible that other systems are also doing it at the same time, but let's take the simpler flow first. Now when it is sending, so some of the servers or all of the servers will respond with RPC itself to that particular S1. So first thing what it does is it voted itself that I am a leader, right? And then others will send the response to S1 if it requested first, right? So here also it is like over RPC, they'll execute the method that you are a leader. So once you receive the response from the majority, then that particular node will be selected as a leader. Once you are selected as a leader, then next thing basically it will do is append log, so which is the real work of these systems. So it will be like it will be another RPC which you are executing about appending the log. And we'll talk about this in the next one. But yeah, now this is the happy path where somebody requested and it executes. The real thing under Raft comes is protocol, what all things comes under this. For example, it's possible that at the same point of time, even though there were different thresholds of time, so in some cycle there are possibility that multiple servers are expecting to be converted into candidate and send the request at the same time to become a leader. In that case, what will happen is, firstly, they will assign themselves as a candidate, and then they are sending it. So, which means server which assigned itself, for example, S5 and S1 at the same time is requesting for election, voting to become the leader, then S1 will definitely not give vote to S5 and the vice versa. So whichever server receives the majority first, at that time, that particular server will become the leader. Here, simple majority wins, right? If by any chance it tied by any case, then what will happen is it actually goes into the initial state where nobody is a leader, and again you have a random time to trigger that, convert yourself into the candidate and ask for the vote. And that is how we try to minimize that state where multiple followers are converting them into candidate and multiple followers are trying to become the leader, right? Otherwise our system will not be into a consistent state. Same thing happens if a leader fails, right? So if a leader failed, that means this append log request is not coming to servers. And that is where the threshold point. So as soon as you are sending that append log request to the server, the threshold point, basically your timer initiates from the zero. And as soon as from this request to next request, if that time period is exhausted, then that server will convert itself into what you can say into a candidate. So in failure scenario also, this is what will happen. I think, yeah, these are the failure scenario, and on a high level, happy path and failure scenario, how to convert any node into a system in a leader, right? So this is how these systems are, you can say, self-sustained to whenever a leader dies or a follower die, how as a unit it is consistent and basically serving highly consistent services to the consumers. So once your leader is elected, now it's the time to do the real job, which is replication of the logs in all of your nodes. So here our main leader is going to make sure that it is replicated in all the nodes, right? So imagine that you are receiving a request, and that request will come from some client. Once a leader is receiving a request, what exactly is happening when you need to replicate it in all the machines which you are having? It will simply use append log RPC, and it is sending it to all the nodes where it need to replicate. So all of them are followers right now because we have a active leader, right? So what will happen is these servers, followers will respond back saying request received, right? So server, the main leader, need to wait for the consensus that majority of the group is successfully received the log. So there are two things happening here. First, it is adding it to it the current log, local log table. So think of it like you have an array, right? And then in that array, you need to append the log first. So maybe till wherever we had, so next index, imagine index 10th, where you need to do the new entry. So here you need to add that new request whichever you have received, but you are appending it in the log. So two things which you need to add here. One is the term. Every So it works in a term, that there was a leader 1 for term 1 and there are leader 2 for term 3, for example. So every leader will have a different term. Whenever a leader is changing, there will be a new term, right? So in this term, and what is my command? Command can be whatever your client want it to be executed, like saving an entry or execute something, but that is least relevant right now. It's just a value for me. So whatever that command is, I will first append it here as a leader. Then I will send the request to all the followers. Followers will respond. Once I have the majority, that majority of followers have received this particular log, then what it need to do now is it need to execute this command, right? This command can be saving this value into the DB or updating some memory or doing anything. Once it is done, then there will be a result of this. Like, for example, if you're adding something, an entry into the cache, then result is success or failure of adding it into the cache. That result, then it will respond back to the client. So this is the happy path where you are appending and responding back after execution. Now, obviously, there will be a lot of cases where either server can die before executing it, right? Or followers can die before executing it, right? So let's follow up on those cases. Those are the more important part of this raft algorithm. So with happy path, what should happen is, let's suppose we have this leader and follower. So imagine that they're maintaining an array, and these are my logs, which we are talking about. What should happen in ideal case, the positive case, which we discussed, that all these entries at both the machines, leader and the follower, have exactly same term. For example, here it can be like my term x, or for simplicity, let's just keep it one again, same term, right? Then two, uh, two, and then three, and nothing here. So exactly same thing should be here. So this is my path where there is no discrepancies between your follower and the leader. Everything is in sync. Now, what exactly happened in the real world scenario? There can be many cases, some of which are like these four cases I mentioned here. For example, so let's suppose my leader had these one, one, two, two, three here. So this is my index, this is my term, and obviously there is a command. So right now, command is irrelevant for Raft, right? It is required for the real application, but for Raft, this is irrelevant because Raft is trying to make sure that same command, same entry is there everywhere. But what is that command? It's not relevant for the Raft per se, right? So let's suppose I am having these things into the leader, but your follower is missing, one of its log entry at this particular index. So it can be like it is having one, 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 two, two, uh, two here as well, and nothing is here. This is missing. So you can say that basically something is missing. So what could have happened is, so when your leader sent this to S3. For example, all others responded back. So majority responded to the server, it commented and responded back to the client. But S3 somehow failed at that particular point of time, hence it is lacking. Right? This can be your one scenario. Another scenario can be same way, multiple entries are missing. So it failed. It might have been failed for some amount of time. Hence, it might have missed multiple entries. For example, maybe this two was also not there. This one was also not there. So multiple entries are missing. And when you will call it a missing, when you are actually calling this command, and then you realize that server is saying, I need to add at this index this particular entry, and you realize that right now follower is trying to add it here because this is where the follower current index is. So that is where the mismatch is, and this is how you can catch it. Now another scenario can be that follower is having extra entries. How can that be? So imagine that this was the leader which sent the entries to S3, and majority failed to respond back to S1, and S1 also died in between, right? In between, S5 became a leader and it sent some entry, and we got forwarded, and S1 comes back as a leader and tried to send the entries again. So what might have happened is that a different server might have sent some request to the S3. So, and when S1 comes back as a leader, it realizes that my follower is actually having an extra entry. For example, at this term, I might be having four as term, and obviously some command. Whereas my current leader, which is S1 now become a leader, is having these entries here, because other it might have not committed, or it might have received majority responses, but before committing that particular thing to its own state, it might have failed, right? But others who have responded successfully, they might have successfully committed them as well in their state. So that way follower can also be ahead. So this is another mismatch. Right now we are only talking about mismatch scenarios. How these will be fixed is something which we'll try to uh, go to. And one more scenario is basically similarly, there can be multiple things ahead, not just like, so there can be mismatches like at this particular thing, there is a term 3, term 3, which is, you can say uncommitted in the your leader, but in follower the entries are there, and then some entries are missing here, right? It is possible that here it is 2 to 3, and then it might have moved to term 4. So first you, what could have happened here is, first your leader sent something, then leader failed, then your new leader came into the picture, it sent some entries, and your follower, this particular follower might have failed at this particular time, hence leader is having these values, but this follower is still trying to follow to the previous leader. So hence there is like a big gap, some extra entries plus missing entries, right? So this can be another scenario which Raft have to take care of it here. How exactly we take care of these scenarios? Actually, solution is kind of pretty simple, that we need to do consistency check between the leader and the follower. So how exactly it happens is that our leader keeps the next index which it needs to write for every follower, right? And let's suppose right now it does not have the index of S1 does not have next index value for S3, for example. So it will assume that the next index for S3 is 6 because still here leader is having the value. So it went ahead. It normally goes ahead with that assumption. So how it will really happen is basically with this next index, assuming that this is my next index, it will go ahead and send the request of append logs, remote RPC, basically a remote procedure call will happen from your leader to the follower, right? Now, because this index at follower is actually 3, right? And your leader is saying that I will write 6. So follower will simply reject this request. In this case, what will happen whenever there is a rejection, what leader need to do is it will reduce, basically it will subtract it index. So it will simply goes to here, that is this the index where things are matching, all right? So it will again reject. Likewise, it will go till here, that here ultimately when you are saying this as your next index, and when follower try to match this, that yes, everything is matching at this index, this is the term value which I am having, which is same as my leader, so it will be a success. So after this, every value will be copied from leader to follower. That is how my leader and follower will be consistent after it. So there will be these many calls after it we need to happen to copy everything, because it's not just the value. What you actually need to copy is for these particular combination of your index and your term value. Ultimately what you need to copy is the operation, the log, what the real value is. So that is what it will do. Ultimately when there will be multiple append log calls, then all the values at every index will be exact identical in your leader and all the followers. Basically this is, you can say, log replication protocol is with the Raft. Log replication, the consistency, basically consensus algorithm is one of the toughest problem which we are having in software world. Now this may look like that this is not very optimized because you are going very linear here, but if you see the point that if any of the follower is dying, or any of the leader is dying, for example, it need not to replay all the entries to come in sync with the other nodes. It is starting from the point where it failed. So that way it is actually very optimized. Having said that, yes, there are you can say more optimization on terms of it can jump to the failure point directly, when follower can reply back where was the mismatch and all those things, but we are not going in that detail. That's not required when you're actually discussing high level of Raft. Now, some more things to mention on this, like I'm talking about optimization. Obviously, your append entries can be in batch, multiple. Normally, it is in batch, right? When multiple entries are there on client, you can say your from your client to your leader, it can replicate those onto all other followers in batching. So that way, things will be faster. Idempotency is one of the you can say most important thing, which is providing it to you. So when you will, let's suppose if there are any kind of failures, then you will send the same request to same follower from the server even 100 times, then also the output will be same. It will not like it will append those things also, because why? Because you are sending the index and term, right? So you will always apply at the same position, that at fifth for third term add this value. So that is how idempotency also it is taken care by this particular protocol in Raft. Heartbeat optimization, all of your followers knows that your leader is there because it is continuously sending your uh, heartbeat requests. So this point I already mentioned. So whenever there is a crash or a restart, so basically it need not to replay from the scratch. It will replay from the point of failure, and the you can say the restarting or recovering from a crash is very optimized with this consensus algorithm. Now, first to summarize about the Raft, whenever you are discussing about the Raft, first is this is an consensus algorithm, right? And the major two protocols which you need to mention in that is that how you will choose a leader whenever there are multiple components in picture, which usually is the case in a distributed system, and how you will replicate the state, replicate the log in all the nodes of that particular system. Safety and fault tolerance also, if asked, if you're going in deep, that we have to talk about. Majorly in this video, we talked about first two. Now think of normally, actually you are asked about, there are rare chances that you will be asked about Raft. But when you are discussing systems like, distributed systems like your X, Twitter, Instagram, YouTube, or any other, normally we are actually talking about distributed systems in design interview. As a senior engineer, uh, you have to talk about how you will provide strong consistency with high availability, right? How is that possible? How you will make sure that it is working in that fashion, plus how you will maintain the coordination, right, between all the nodes. That is where think of things, right, that in your design, let's suppose you have a metadata store or a configuration service, right? For example, that you are managing which instance owns which partition. And I'll give the example there. So just think of, out of all these instances, if you're talking about metadata store, which instance, is in which partition, right? And this basically these things you have to talk about, like I said, highly available but highly consistent as well, not eventually consistent, highly consistent, right? So in That is where in distributed system you'll say, I'll use a coordination service, right? Like etcd, which is in Kubernetes, right? Which internally will use Raft. So that is where you can mention the Raft, and if people are going in detail, so you have a little bit details of it now. So yeah, so basically mentioning that for a senior engineer, is kind of a detail which you are adding, which you should be, that you know the internals of it. Think of Twitter, for example, right? So in system like Twitter, there is a timeline service, which normally fetches tweets of all the people you follow, right? Build your home timeline and then do ranking and all those things on it. That particular service, because you are doing it at that scale, is obviously not running on one particular server. So it is normally running on in a distributed fashion in different different nodes, and normally those nodes have to be sharded, so they are sharded by any fashion, right? By user id reason, they can be different, you can say logic behind it, how you sharded your nodes. There also we do need that there should be one, you can say master or a leader service, right? When you need that one leader or one master, so your leader election will ultimately be done by a consensus algorithm, and that is where Raft can come in picture, right? So yeah, so this is just one example. In every system design, a distributed system, there will be many scenarios where you will need a consensus algorithm and where you can bring up about Raft. I think this is about consensus and especially about the Raft. That's it. Thank you.